Hi everybody. I want to give you some basic queuing results for the MM1 queue. And first thing I'd like to do is describe what queuing theory is and why it's important. In general, it is able to describe a random process, or what some people will call a stochastic process. And what we're going to do is we're going to assume that we have a memoryless process with Poisson arrivals and exponentially distributed service times. We'll cover Little's formula this time in a little bit more depth, and then we'll talk about the birth-death process. We have a notation known as Kendall notation. This is the ABC notation, where A indicates the probability distribution function for arrivals. B is your probability distribution for the service time. C is the number of parallel servers. M means it's a Markovian, exponential, or memoryless process. D stands for deterministic, and G stands for general distribution. So queuing systems with exponentially distributed service and inter-arrival times with C servers, these are going to be MMC queues, and we're going to focus on a single server, so that would be an MM1 queue. So now we have Poisson arrival, exponential service, and a single queue. What we'd like to observe is that this is not suitable for uniform processing time. For that, we would use an MD1 queue, where processing time is symbolized by the D, or deterministic time. So this is one of the basic restrictions. Also, we have a memoryless process, and so we assume that a customer's arrival is not impacted, or is not going to impact on what happens for the next customer. So in other words, we do not have what we call a queue with discouragement. Another property is that we have independent, exponentially distributed random variables, that the sum of the distributed functions is also a distributed function, that the arrival rates can therefore be added linearly, that the service rates can be added linearly, and that in aggregate, the average service rate will be represented by mu, and the average arrival rate will be represented by lambda. So we're familiar with the Poisson distribution. In the case of arrival rates, we would substitute lambda for alpha t, and we would put lambda in for the arrival, and mu in for the service time. So if we have an aggregate of Poisson processes, we can take an addition of all of the arrival rates to come up with an aggregate arrival rate. Similarly, when we treat the probability of having 1 in the system versus 2 in the system versus n in the system, all of those probabilities must sum to 1. And in general, the arrival rate for the ith state is going to be equal to the probability in the ith of being in the ith state times the overall arrival rate. So now we can focus in on the number of customers in the queue. The lambda sub n will be the arrival rate for the number of arrivals per unit time at when there are n in the system. And so what we can do is we can assign an arrival rate for each number in the queue. So if there's 10 in the system, we'd have lambda sub n, and then service rate with 10 in the system would be mu sub n. Rho will be our intensity level, and so that would be a ratio of lambda over mu. And P sub n is the probability that there are n customers in the system at a given time. So with the intensity represented by lambda over mu, we could say that this is the capacity demand, number of customers per second, versus available capacity, the number of customers we can process in a given unit of time. And presumably rho is less than 1 for a steady state system. And if there were C servers in the system, then our rho would be changed to look at the aggregate lambda over mu, but we would then divide that by the total number of servers. So presumably 10 servers would improve the capacity by a factor of 10. So with steady state systems, we should be able to do a steady state analysis as we go from one transition state into another. Transient systems will cause burstiness in our queue and in our overall system, but these transients will eventually die out. So here's an example where we can see the transients causing some sort of bursty arrivals and then service, and then in principle it averages it out to the area which is the expected number in the queue over a period of time. So the probability that there are n customers in the queue will represent as p sub n as t goes to infinity. This will be the steady state. L will be the expected number of customers in the system. That's both in the queue and in service. L sub q, that'll be the number of customers in the queue. W will be our expected waiting time in the system. That includes in the queue and in service. Then W sub q must be the expected time a job spends just in the queue. That's how much time you spend waiting. And so now we can use Little's relationship, which says L, the number of customers in the system, is going to be equal to the arrival rate times the amount of time spent waiting. And then the number of customers in the queue will be equal to the arrival rate times the amount of time spent waiting in the queue. And so if we average up the total numbers of lambda, which are represented by the probability that a certain number of customers are in the system times the arrival rate for that particular state in the system, we'll get an average lambda. So the foundation is that we have a birth-death relationship, and what we want to do is attempt to perform what's called detailed balance equations. And in detailed balance equations, we're given a specific state and we want to see what the transitions are out of that state and back into the state in the case where we have lambda over mu less than 1. So this is a Markov chain. And so the Markov chain, which is shown in here, says if I'm in state 0, my departure from state 0 will be at a rate of lambda 0. My arrival back to state 0 will be at a rate of mu sub 1. And presumably we can get some measurement for this for each one of the states. And we can continue on until we have perhaps characterized the entire Markov chain for all n states. And so my assumption is we have an infinite population that can arrive. It's arriving with Poisson distribution. There's no renegotiating. There's no, we'll call it Q with discouragement or bulking. We have a first in, first out discipline. And the mu, expected service rate, when the server is busy, is unchanged as a function of time. So in the steady state, we provide the detailed balance equations for every state n. So the rate in should equal the rate out in principle, and the average entrance rate should equal the average departure rate, and moreover, all the probabilities for being in any specific state will sum to 1. So if we know the probability of being in state 1 is going to equal to the arrival for state 0, and departure for state 1 will equal arrival for state 0, then we can solve for P1 and we can come up with a ratio for mu over for lambda over mu. And we can do this in terms of every prior state. But having said that, Once we do that sort of recursive relation, that iterative relation, we can then back substitute. And once we do that kind of back substitution, we see that we have an exponentially growing number as a function of the ratio between lambda over mu. Moreover, we know that all of the p sub i's should sum to 1. And if all the p sub i's are going to sum to 1, we can solve this problem if we assume every lambda and every mu is the same. That is, let's assume the probability of arrival into any given state is equal to the probability of departure from any given state. And these things are all the same throughout all the different states. So if that happens, then it's lambda over mu plus lambda squared over mu squared plus lambda cubed over mu cubed, dot, dot, dot. And then what happens is you have rho, where rho is equal to lambda over mu to the k, and that's being added up times p0. There's your p0, which can come out. And then now you have the sum of rho to the k, which is a geometric series and is equal to 1 over 1 minus rho. So now you've got 1 over 1 minus rho times p0 equals 1. So having said that, with rho equal to lambda over mu, I've got p0 equals 1 minus rho, and this is the basic result. I've got pn, that is the probability of being in any state n, is equal to rho to the n times 1 minus rho. And then the probability that n is greater than k is just rho to the k. And now I've got interesting results from Little's equation that says that rho is divided by 1 over rho, 1 minus rho, is equal to the total number of people in the system, or jobs in the system. Moreover, once I have this, I can use Little's equation to compute the waiting time, because waiting time times lambda is going to be the total number of people in the system. I can solve for the waiting time and then back substitute in for L, and now I've got 1 divided by mu minus lambda for my waiting time, on average, in the system. The amount of time I spend in the queue is going to be the amount of time, the number of people in the queue is going to be equal to the number of people in the system minus the person who's being serviced on average. And so what we've got is lambda equal to rho over 1 minus rho, and then subtract off rho, and that becomes rho squared divided by 1 minus rho. Moreover, the number of people in the queue is waiting in the queue is going to be equal to the number of people waiting in the system minus the person being served, and we know the service time is going to be 1 over mu, so we just have to subtract off 1 over mu from 1 over mu minus lambda, and that gives us lambda over mu times mu minus lambda. So these results are the results that you can use for your computations, and they're perhaps one of the more fundamental results that you can get from both Little's theorem and also for the detailed balance equations. And here's how you apply it. Here we'll start with the average arrival rate of 5 customers per hour in a banking system, and we'll service 6 customers per hour. That's 1 customer every 10 minutes. And we're going to use our knowledge of queuing theory, and we'll get rho, which is lambda over mu, and that's going to be 5 over 6, or 0.83. We'll get L sub q, and if we go back, we can see L sub q is going to be L minus rho, where L is equal to rho divided by 1 minus rho. So we know rho. We can now find L. Once we have L, we can subtract off rho, and now we can get L sub q. And figuring that out allows us to come up with an average number of people waiting, 4.2. Moreover, we can get their waiting time if we know how many there are. We just divide by the arrival rate, and that will give us 0.83, which is in hours, 0.83 hours. That's kind of a long time to be waiting, I think. So 5 customers are coming in per hour, but you're only servicing 6 customers per hour. So maybe that's not an unreasonable amount of waiting time given the numbers. Probably what you need are more tellers to reduce the number, to increase the number of customers per hour and reduce the waiting time. And so that's what I've got for you for today. These are your basic equations. These are probably equations you want to write down and take note of, and they're the ones that you'll be using for solving some of your MM1 problems in the future. Thank you.